In a previous video, I looked at undamped oscillators, and then I did a derivation of damped oscillators. And that video will be down below. I can't go over the whole thing because it's already 30 minutes. But what I want to do is look at three special cases for the damped oscillator, the damped harmonic oscillator. And those three cases are underdamped, overdamped, and critically damped. So just a quick review. Suppose I have a mass on a spring in one dimension, and so that when you pull this mass, there's a restoring spring force, but there's also a force that depends on the velocity. So imagine it's moving through oil or something like that. So the total force would be negative kx, that's the force due to the spring, minus bx dot. So x dot is the velocity. Dot, we use dot notation for derivatives with respect to time. So k is the spring constant, b is some parameter that deals with the viscosity and the size and all that other stuff. It's the proportional constant for the force and velocity. So this is equal to mass times acceleration, x double dot. And then from there you can solve for x double dot. We make some substitutions. One is to say that if I have no dampening force, I find this is the frequency of oscillation omega naught, that's an omega, square root of k over m. So we're going to use that term, it's very useful. And then beta we're going to use as the parameter b over m, but we multiply by 2. Why? When we set up the quadratic equation to solve these differential equations, it allows us to factor out a 2 and 2's all cancel. You don't have to do that, but I would recommend that you do. It just makes it simpler. And from that, we found the following solution to the differential equation. You actually get two solutions because it's a second order differential, and the linear combination of those solutions is a solution. And so we can write it like this. X as a function of t is e to the negative beta t, so this is a decay parameter. And then I have some constant that depends on initial conditions, e to the square root of beta squared minus omega naught squared t, and constant e to the negative square root of beta squared minus omega naught t. So that's my solution. I already did that, and you can go back and look at that video. But now we want to look at three special cases, because this could be three different things. And I did this already, but we're going to do it again. And the first is, what if it is underdamped? So let's look at underdamped. In the case of an underdamped motion, so we'll call this underdamped. You could call it weakly damped if you want. Underdamped. In that case, the square root of beta squared minus omega naught squared is imaginary. Imaginary. And that would be the case if beta squared is less than omega naught squared. In that case, when I take beta squared minus omega naught squared, I can get a negative number. But then I take the square root and bam-o, you get an imaginary number. In the exponent, okay, it's not an imaginary number, it's an imaginary number in the exponent, which is a little bit different. So what we did was to say, okay, what if I go ahead and change the order of this? So I can write this as the square root of negative omega naught squared minus beta. That's the same thing. And then I have a negative 1 that I factor out of there, and I get that I. I times the square root of omega naught squared minus beta. And then we can call this I omega 1. So omega 1 would be the square root of omega naught squared minus beta squared. So it's just a frequency. So in that case, I can rewrite my solution as the following. X is the function of t. I still have that e to the negative beta t. C1, e to the, now I have e to the I omega 1. Right, so it's going to be e to the I omega 1 t, where I replace that whole square root with just omega 1, plus C2 e to the negative I omega 1 t. And I'm not going to show it, but this, if I have e to the I omega t, or e to the I theta plus e to the minus I theta, you can actually write that in terms of sines and cosines. And so this is mathematically equivalent to, and I showed this in another video linked down below. I should make a whole playlist for this whole thing. E to the negative beta t, and then I'm going to get a cosine omega 1t plus b sine omega 1t. And then the a and the b depend on the initial conditions. So, but we can think of this as an oscillating term. This is an oscillation, and a decaying term. So let's go ahead and plot this. I actually want to plot this, and then the product of the two. Because everyone makes that picture, and I want to show it in Python because I want to, and you can't stop me. Okay, so let's just jump over to Python. I actually got a slight head start on this, and I apologize. I just didn't want to waste time typing in stuff. So here we are in Python. I'm using GlowScript vPython in trinket.io. And this allows me to make a graph and do some calculations. I've already made 3 graphs that I'm going to plot. So FE is the exponential decay. And I saw a picture of this where it's like dotted, and so I'm going to make that dotted. And then FO is my oscillating term. FX is going to be my my total term. So I'm going to plot those 3 things. So the exponential is going to be blue, the oscillation is going to be green, and then the whole thing will be red. Okay, so I've already got some terms in here. So I have T, I have dt, the mass, B, K, actually K is 5, that's fine. X0 is where it starts, the initial x position, initial velocity is 0. That's going to make that one term. If I go back to that sines and cosines, I'm going to have A is going to be x naught, and B is V0 over omega. So I'm not going to have a sine term, and I hope that's okay. Oh, yeah, I am doing it that way. Okay. Am I doing it that way? Yeah. Okay, so let's go ahead and calculate my... Do I need the beta term? Yeah, I do. So let's say beta, I'm using B for beta. Beta is B divided by 2 times M. I need omega 0 equals the square root of K over M. I'm also going to need that omega 1 term. Omega 1 is equal to the square root of beta squared minus omega naught squared. Okay. That's right. So let's just plot that exponential term. That's all I'm going to do. Okay, so let's say while t is less than 3. Can you see this? Make it a little bit bigger. Too big. Okay, that's good. So there we have that. While t is less than 3, the first thing I need to do is to calculate this exponential term. So let's call that, let's call it DEC for, what did I call it DEC? I'm not sure why I called it that. I don't know, that's fine. So it's just going to be exponential negative beta times t. And then I'm going to plot that, so that's fe.plot t DEC, and then I'm going to increase t. T equals t plus dt. And let's just do that. Let's just see if this works out okay. One step at a time. You got to do one thing at a time. Okay, so I want to make that dotted, and it actually is dotted because I use G dots. But the problem is I have a time step of dt of 0.0001, so they're really, really close together. So let's make another time step. I want a longer time step for this, just to make the dot spread out. But I want a higher time step for the others. So I'm actually going to make 2 loops. So let's go ahead and make a second time step, dt2 of 0.1. And then I'm just going to change this to dt2. And it should still work, but the dots will be spread out more. Okay, that's pretty good. Now, that's the top thing, right? But I actually want to have, there's a upper and bound on both the positive and the negative side of the function. So I need to replot this in the negative direction, which is easy to do. I can use the same function. I can just say fe.plot t negative DEC. So it's going to plot 2 points every time, one positive, one negative. And what do we get? Okay, now I'm going to make one more change, and it's just a little bit weird. I'll do it in a second, though. Okay, so now let's go plot the oscillation term. So let's go back down here and make a new loop because I want to change the time step. So I'm going to say t equals 0 again. And then while t is less than 3. Now I'm going to calculate the oscillations. Let's call it OSC equals x0 times cosine omega 1 times t. That's it. Now I'm going to plot that what do I call it? FO dot plot T oscillation, and then add 1 to T. That's that. Okay, let's see what that looks like. Nothing. Wow, T is less than 3. Why didn't it calculate anything? It didn't plot that. FO dot plot. FO dot plot. What did I do wrong? T equals 0 while T is less than 3. Cosine omega 1, which I have omega 1. Print W1. I'm just curious what's happening. Beta is, it's not a number because B is 0.1 K is, I think I put 10. Why is it not a number? Okay, let's see. Print B. Print omega 0. K over M. Oh, I know why, because I got this backwards. I said omega. It's an imaginary number. Yeah, I had it right over here in the paper. Okay, I'm going to change this back to 5 because that's what I wanted. Okay. Done. Okay, so now you see one problem. My oscillation goes from x0 to negative x0, which is small, but my exponential, it starts out at 1. And that's fine. I'm going to actually multiply the exponential by x02 just because it looks a lot better. So down here, that's a pretty good graph though, right there, don't you think? I'm not sure why. Let's see. Move that over a little bit. That's better. So let's go down here and multiply this by x0. And let's see what that looks like now. See, now that kind of looks better. So we're going to multiply those two functions together, not really, and then plot the total. Did I not save this? Underdamped oscillator. I'm going to give you the code. Don't worry about it. You will get your code. But you really should do it yourself. I mean, I'm just saying, if you like watch my video and type that out yourself, you're really going to understand it. If you just take the code and edit it, it's like me solving a puzzle for you and giving it to you. You really need to, you would be amazed. Actually, just typing the code yourself does help out a lot. That's what I recommend, but you do it, you be you. Okay, I'm not going to make you do what you don't want to do. Okay, finally, I'm going to plot the function xp equals, it's just a whole thing. It's going to be exponent negative b times t times x0 times cosine omega 1 times t. And then let's plot that. And I called it fx. Did I call it fx? Yeah. Dot plot t xp. And that's xp for the x plot. I mean, that is art. That's art right there. Okay, but I do want to show you one more thing in there. This is that picture you get from the book, and you see that we made it with our own Python code, and it's always better to make things yourself. Now, this is not the same as a damped, if just an exponential amplitude of an undamped oscillator. Because remember, the frequency of oscillation is omega 1, not omega. So let's just plot. Let's go down here for our oscillating function. I'm going to just use omega 0, and you can kind of see that they are indeed different. Notice right here that these peaks are lined up. Peaks are lined up. They have the same frequency. But if I change that, now I'm plotting omega 0, the peaks are not quite lined up. They're not. They look lined up, but they're not. I don't think, well, my beta is really small. Okay, just trust me on that one. Maybe that one didn't work out too well. Okay, so that's underdamped. Now let's switch over to overdamped oscillations. Switching back to the paper view. Okay, overdamped. So overdamped, you got to write it out, otherwise it doesn't actually happen. So for overdamped, I have beta greater than omega naught. So if that's the case, then I can write x as a function of t like this. X equals e to the negative beta t. That's the same thing. Now I can write c1 e to the square root of beta squared minus omega naught squared t. That's an exponential term. Plus c2 times, oops, I don't need that parentheses, e to the negative square root of beta squared minus omega naught squared t. So it's not an oscillation. There's no oscillations. Why do I have oscillations before? It was because I had an imaginary number in the exponent, and that turned it into sines and cosines. I no longer have that. This is an exponentially growing term because it's positive. This is an exponentially decaying term, but they're both multiplied by an exponentially decaying term. So let's just go ahead and plot this thing. Let's just do it. Okay, I'm going to actually copy this code, save it, because I don't want to mess up that graph. That graph is so pretty that it can't ever be touched. Okay. Oh, I need to switch back over to your computer view. Okay, so saving that graph. That graph is saved. Now let's copy this and then make a second set of data, just so we don't mess it up. I'm going to use the same parameters, but I am going to change some stuff. So down here, the first thing I need to do is to change b, right? So I want to make sure that beta squared is greater than omega. So I'm going to change this to 0.5. I'm going to try and change k to 0.5. I think that should work. I'm just checking my other values, v. So let's print those out now. There's b, there's omega. I don't want to do this one now because that one's going to be imaginary. Let's print b and omega naught. Let's just beta. That's beta. Okay, let's print them both. I don't need this function. And let's just get rid of all this stuff. I don't want to do that yet. Okay, so let's just print those, make sure. Okay, so b is 5, omega 0 is 3. So I am in the case where the term under the square root in the exponent is positive. It's not imaginary. Well, it's real. Okay. So now the one thing that I need to do here is I do need these C1 and C2 terms. Let's just pick C1 equals x0 over 2 and C2 equals x0 over 2. We can change this later. Okay, I'm just going to pick that. And I think that should work. So I have B, I have omega naught, I have C1, I have C2. I'm going to plot, I'm just going to plot FE. I'm going to change it to G curve. And that will be my, let's call it FC. FO. Let's use FO for overdamped. Is it O, right? Overdamped. Okay, so I've changed it to blue. I like blue and red. So I have that. Now I have C1, I have C2. All I need to do is just calculate the thing. So I'm going to go down here. I don't need t equals 0 again. So I'm just going to say while t is less than 3. The first thing I need to do is to calculate that. So I'm just going to say xp equals exponent negative b times t times c1 times e to exponent of the square root of b squared. I should have put this as a constant. B squared minus omega naught squared. Omega naught squared. All of that after I get out of the square root. Yeah. Times t. And then that's raised to the point. And then, okay, yeah. And then I'm going to do the same thing for C2. So I'm just going to copy this. Plus C2. But that C, it's going to be negative square root. And it's going to be C2. Although C1 and C2 are the same thing in this case. And that's fine. Okay, so there we have that. Now let's plot it. So FO dot plot T XP and then increase T. T equals T plus TT. And let's see what we get. Okay, so I'm pretty cool with that. That's, you pull the mass out to the side, let it go. What if you want to make, like, it starts at x equals 0, but has some velocity, we can do that. You just got to change these parameters up here. Let's just make C2 negative. I think that will do it. Because then the position will be 0 to begin with, but when you take the derivative, you get a non-zero term. Yeah, so it starts at the origins, ejected out, and then it goes and comes back. So it does get an oscillation, but it eventually stops. It's going to stop back at x equals 0 because if it's not at x equals 0, there's going to be a force. It has to be stopped, and the force has to be 0. And so stopped, there's going to be no drag force. And the only way that you could have a 0 spring force is to be at x equals 0. So it has to end up there. Okay, let's just go back to the case where it starts off to the side. Okay, that's that. So that's overdamped. There's no oscillations unless you want to count that as one oscillation. That's fine. If you interesting choices of parameters, you can get it like go under the x-axis and back, but it's not an oscillation. It's just a sum of exponentials. Okay, so now let's look at the last case. Switching back over to paper, I'm going to use the same graph over here, paper view, and that's going to be critically damped. Critically, is that 2 L's? I don't know. Damped. And this is the case where beta equals omega naught. So if I put in beta equals omega naught, I get this. X is a function of time is e to the negative beta t. And then this term, this is going to be beta minus omega naught, but they're the same, that's 0. So e to the 0 is 1. So I just get C1, and over here I get e to the 0 plus C2. That's it. So it's just an exponential decay term. That one's pretty easy to plot. So let's go plot that over here on the computer in the same thing. So I have fx. Let's call it fx. Let's call it fc for critical. Okay, so let's just plot that down here. We can calculate both of those. I'm going to go xpc for critical. It's going to be exp times to the negative beta t times C1 plus C2. That's it. So this is the same initial condition C1 and C2, but I've adjusted the parameters so that beta is equal to omega naught. And then let's plot that. So fc.plot t xpc. And it decays and stops too. But you'll notice this is just a pure decay. There's not any kind of fighting between the terms, right? You're not going to get any weird things. And I should point out that if I start with a velocity at the position, I could get it to work somehow. But that's fine. The important point is that no matter what you do, the critical damped is going to stop faster. It's the fastest way to stop. It's the fastest way to get the whole thing to stop. You can't beat it with the overdamped. It just doesn't happen. Okay, so underdamped, overdamped, critically damped, plotting in Python. Most important thing to remember is that I made that awesome graph. You remember that. I'm going to make a playlist of all these things. I'll get the playlist down below for my simple harmonic oscillator, the 3 cases. How do you calculate a damped oscillator? It's all going to be there. I got a couple more. I'm going to do oscillators with phase space, but I'm not sure when I get to that. But I will get to it, and I'll talk to you later.